So hey everyone, this is part 1 of my video series covering how to use Trangium's batch solver. This is a super cool and very useful website for generating algs, particularly large alg sets at once, versus having to manually gen algs for each particular case. So in this video, I'm going to go over the basics and what each field is, because this solver has a lot of functionality, but it also has a lot of different things for you to input your parameters, and so it can get complicated if you want it to be complicated and do complicated things. And so the learning curve might seem high, and it's not exactly the most intuitive thing. So I wanted to make this series to explain how to use this solver, because it's a super useful tool once you know how to use it, and it's really not too hard to learn. You just have to have somebody show you, basically. So this is what this is for. Like I said earlier, this is to cover the basics of using this solver, and I will have future videos to go more in depth on more advanced things you can do with the solver, or more niche things that not everybody will probably need for most of their needs. So let's get into it. So to explain what this is for, it's for genning algs in batches, thus the name batch solver. So for example, instead of having to gen every single case in ZBLL one by one, like you might have to do in something like Cube Explorer, you can write a custom scramble, which we'll talk about later, that will let you gen all of ZBLL once you set it up, and just let it run, and it will gen all the algs for you. So it's very useful. So let's start with the first field here, which is the puzzle section. This one's pretty easy. By default, when you load the batch solver website, it will preload the 3x3 puzzle definition. And this is just what tells the solver what moves do what. It's what defines the puzzle to the solver. Most people are going to be using this for 3x3. And so if you are going to use this to gen algs for a 3x3, you just leave this section alone. However, this solver does support other puzzles, and so we have a few definitions preloaded: 3x3, 2x2, skewed, pyraminx, megaminx, and there's also an option for custom where you can write your own definitions. I actually wrote the megaminx definition for the solver, and so in the future, I will show a video going over how to write custom puzzle definitions as well. So that's the basics of this puzzle section. Not a whole lot to it. So now let's get into something interesting: the unique orientations and equivalences section. So in this box, this is where you input information to the solver regarding pieces that are equivalent to each other, so you don't have to worry about the permutation of those pieces, and also where you tell the solver what pieces do not need to be oriented. So for example, if you wanted to gen algs for OLL, you do not care unless you're genning pure OLL, but if you're just genning normal algs for OLL, you don't care what PLL it applies to the last layer. So in other words, you don't care what it does to the permutation of the last layer edges and corners, only the orientation. In which case, you would put this into this field, which is saying the 4 edges of the last layer are equivalent to each other, and the 4 corners of the last layer are equivalent to each other. So they can be in any of each other's spots. It doesn't matter. Similarly, we can tell the solver we want to ignore the orientation of pieces. So for example, if I put this in here, hit enter. Okay, so we would put something like this in here to tell the solver how to generate ZBLS, which, if you don't know, is an alg set for your last slot for CFOP, where you solve your last slot and you orient the edges of the last layer so that way you can do ZBLL. So here we see, like in the OLL section, the 4 edges are equivalent to each other because we don't care which edges are where, only that they're oriented. But we don't care about the permutation of the corners, but they also do not have to be oriented because this is ZBLL. So we put 1 and then a colon, and then in curly brackets the pieces that do not have to be oriented. I think I failed to mention this earlier, but you put pieces that are equivalent to each other in curly brackets. And then for orientation, you place a 1 and a colon before that set of brackets for pieces that do not need to be oriented. You should also not mix piece types, of course. It wouldn't make sense to put a corner being equivalent to an edge, for example. So now we get into a part that takes a little bit of explaining, I think, but I'll try to trim down my explanation for this. So this is the prune, search, and subgroup section. And so what this does is it tells the solver what moves do you want the algs to be ginned in, and then how long do you want the algs, or what length of alg do you want the max length to be for the solver to look for. So for example, you might tell the solver you want to look for RUF ZBLLs that are up to 15 moves long. So prune and search, when you add the two numbers you put in here, because you have to put numbers here, kind of. I'll explain more on that in a second. But for now, just know, let's say we put numbers here. The sum of those numbers is going to be the length of the alg the solver will search for, all the way up to. And then the subgroup is just where you put the moves you want. So for example, if we want RUF ZBLL, we put R space U space F, or you could put R comma U comma F. It doesn't matter, it's just each move has to be separated either by comma or space. I like to just put spacings because we have lots of room to do so. But that's all the subgroup section is for, is you just put the moves you want it to check for algorithms in. So let's talk about these two now. Prune is hardware dependent. So prune, what values you can put in the prune section depends on the move group and on the amount of RAM your computer has. So to explain why, let's take a look at this short example. So let's set the move group RUF, and we'll use this for a lot of our examples now. If we go over here, the way prune works is it stores in the RAM all the states of the cube that can be solved by any combination of your subgroups or moves up to whatever that prune value is. So for example, if we set prune to be 1 and our subgroup is RUF at depth, for RUF at depth 1, as you can see over here, the possible solutions one move away from solved that are using RUF moves is U, U prime, U2, R, R prime, R2, and F, F prime, F2. If we bump this up to depth 2, we get all two move combinations, right? So UR, UR prime, UR2, U prime R, U prime R prime, U prime R2, and you get the idea. You can see all the different combinations. So if you put 2, it would store all of this in the RAM. If you put depth 3, it would have all 3 move combinations. So you can see it gets larger and larger the higher the number you put. So the larger the prune value you select, the more states it will need to store, and so the more RAM it will need to use. Similarly, it is also tied to the subgroup or whatever move group you choose. So if you only used UR, URUALGs, or whatever, if that's all you're checking for, at a depth 1, you can see it's smaller than the URF subgroup, right? U prime, U2, R prime, R2. It's 3 elements less than when we were using RUF at the same depth. And at that same depth again, depth 1, if we say RULF, now we've added 3 more elements. So you can see at each stage, the amount of elements or states possible or solutions possible for your prune value is also going to depend on your subgroup. So if you put a very large subgroup, like if you wanted to check for every single move, your prune value has to be very low so you don't use too much RAM or run out of memory, because it increases very, very quickly how many possible combinations, move combinations there are, and thus solutions to check for. So basically you need to know there's a trade-off between having a high prune value, which speeds up the solver, and having a larger subgroup or move group that you are checking for algs in. So here you can see this is a message or like a recommendation that Trangium, the person who has written this solver, suggested. So for 2gen, prune can be up to 11 or 12, and so can the search, prune and search values, by the way. 3gen, about 7 or 8, 4gen, 5 to 6, and then 5gen or higher, prune about 4 or 5. So for reference, on my computer, I have 16 gigabytes of RAM. I have found I can get away with up to prune 9 for RUF or 3gen. But anything beyond that, it starts to slow down significantly. So 9 is the absolute limit of what you could use for 3gen, at least with 16 gigabytes of RAM in my experience. And then, so now that we have an idea on how to pick our subgroup and prune and the trade-off between them, now for your search value, it's pretty simple. You just have to look at what length of algs you want checked, and then subtract the prune value from that, and that will give you the search value you need. Sorry, I just blanked out on the word, even though I'm staring at it. So let's say we want RUFZBLL, and let's use a prune value of 7. Now let's say we want it to look for algs that are up to 15 moves. 15 minus 7, that gives us 8. So we would put 8 for our search value. It's that simple. I want to also note, you can also put the number of states instead of prune, or instead of direct numbers. So 1 gigabyte of RAM can store about 5 million states. So if you wanted to allocate only a certain amount of memory usage to the batch solver, you can do so. So let's say you only have 4 gigabytes of RAM and you want the batch solver to only use 2 gigabytes. You can do 2 times 5 million, and that will give you, of course, 10 million states you can store with the 2 gigabytes of RAM. So then you would put 10M, and that will give you your prune value as well if you wanted to go by the amount of states being stored. Alright, so that was quite a long explanation, but for something pretty simple really. So let me skip over the scramble section for a moment and talk about this section here, the pre-adjustment and post-adjustment. So what this does is it tells the solver what face can it adjust before an alg or checking for solutions, and what face can it adjust afterwards. So typically, if you're genning last layer algorithms, you would leave these as U because you want to allow the solver to do U moves before checking for a solution, and then you want it to be able to have U moves available to then realign the cube. So this is like, so leaving U here says we enable AUS before and after the alg, but depending on what you are genning, you might have like an adjust right face or an adjust the front face or whatever it is. Or if it's like RU, EOL or B or whatever, you might have like adjust M layers potentially. So that's something to keep in mind. It's pretty quick and simple case. And the reason I wanted to mention this before scrambling, or the Scramble Field, is that your total search length between prune and search will ignore your pre-AUF number. So what do I mean? So here our subgroup is RUF, and we allow U moves as our AUF. And so you can find, and the total here is 15. But if there's an alg that's like U2 and then 15 moves, because the U2 is at the front and we chose U as our adjustment, it will not count that first U2 move towards the total alg length searched. So that's also something to keep in mind. The batch solver also will not produce algs if it goes through the solved state, because it would be silly to do so. Like if it brings you through solved, why would you break the solved state? So it will not produce algs that pass through the solved state either. Alright, so that was a lot of explaining. So now let's get into the fun part, the really, really cool part that also can get really confusing for people, and that's the scramble field. So this is where you define to the solver what cube state you want solved. So for example, if I type in r u r prime u r u u2 r prime, that's obviously the soon alg. And so this would apply the soon alg to, say, just pretend there's an imaginary cube and you do a soon on the solved cube. What do you get? It will give you anti-soon. And so the case it will try to solve is anti-soon. So if we run this, you see one case shows up here. It will check all the way up through depth 7 when we run the search. And here in just a moment, it will start producing algs that solve anti-soon. As you can see here, we have anti-soon, the alg for it, a bunch of different algs that solve the case. So, if you wanted to solve a single case, you can do so. So how this works is that the scramble field reads from left to right in a linear order. And so if you put plain text here, so if you put just an alg directly in the scramble field, just like I did, or a move, it will apply all those moves and then attempt to solve whatever case is left, as you saw there. If we put U and soon in curly bracket, or sorry, not curly brackets, angled brackets, this tells the solver generate all possible combinations on the cube that you can make from whatever is inside the curly brackets that's separated by commas, whether it's a move or an algorithm. And so using combinations of U moves and soon, we can cover okay, that's not a good example because I need to put something here. So let me show you what PLL is. That will be a better example. So here we have U, a J perm, and a U perm. So by placing these three things inside of angled brackets, we can tell the solver we want to generate all of PLL. So if we scroll down here and I click Start Search, oh, I forgot to put, I cleared this field for some reason. Sorry about that. Now that we ran it and I fixed that mistake, you can see it does indeed calculate. There are 21 possible cases for PLL because we have U moves to adjust the U layer angles between executions. We have JPerm, which will allow us to change the CP so we can have ePLL, AdPLL, and diagPLL. And then we have UPerms, a UPerm, which we can use combinations of UPerm to reach each PLL within the CP. So having these angle brackets that you find combinations of things is incredibly powerful. So let's go back to our previous example. If we wanted to gen OLL, we place this definition here, which again just tells the solver the last layer pieces are equivalent, so it doesn't matter how they're permuted. And then here we put in the solver for the scramble within these angled brackets, U, soon, and edge flip, pure edge flip. So we can reach every combination of OLL. So if we hit Start Search, just like that, you can see it does calculate there are 57 OLLs to gen. So now let's get into another example. I should not have cleared this. To show how this is linear, you can use combinations to gen things like winter variation. So if we put this here, this first part is U and soon, so it'll find all combinations. So this will give us the 7 OLL cases that have all the edges oriented. And then it will do RU, R prime, U prime. So what that will do is it will take the front right pair out of the solved cube. And so this should generate 27 winter variation cases. So if we hit start search, you can see it does calculate the 27 cases. So you can see here that it does in fact run left to right. So it generates all possible cases from this combos, or every combo from these two elements that are in the braces. And then it does this sequence of moves for each one. So now let's move back to ZBLL as our example. I will put this definition in here. This is just PLL and then pure soon, so we can generate all the cases. It didn't have to be pure soon, I just felt like it. So when we run this search, it will produce 493 cases. It will first, you can see here for larger sets, it will calculate all possible cases and then reduce it from mirrors and inverses and all that sorts of stuff into the actual unique number of cases, which is very cool. So now while this runs, actually, let me stop this real quick. I want to cover case sorting. So if you're generating a very large algorithm set, you probably don't want the algs to generate in a random order. That makes finding and organizing the algs in a sheet really, really annoying. So let's quickly talk about how to do case sorting. So in the context of ZBLL, we probably want to sort the cases by the order of corner orientation. So for example, we want U set ZBLL, then T set, and so on. So we would set orientation at, and then place the 4 corners. So this tells the solver we want to also sort all the cases by the orientation of the pieces at UFR, UFL, UBL, UBR, which is of course our 4 last layer corners. So now when we run it, it will then gen algorithms in the order of OCLL. And there's lots of other things: orientation of pieces, and permutation of pieces, and permutation at locations as well. And you can also use this plus sign, so you can add multiple things. So you could do orientation of the corners as well as the permutation of them and that sort of thing, which is super nice. I forgot to mention this earlier. You can also set the solver to gen or check for multiple subgroups. So maybe you want to gen RUF algs and RUL algs. You can just add more move groups, and once it runs the first set, it will check the next one. Obviously, you're not going to see this because it will take a little bit of time to generate all 493 cases RUF, and then it'll move to the RUL. But that's just something to know as well. You can add multiple subgroups or remove them if need be, just like you can add multiple case sorting rules. So it's very cool. So now we move into the options. There are many different options down here. So the first one is how it sorts the actual algorithms instead of the cases. Personally, I like to use STM and then MCC. So the 3 options you have, and you can sort by 2 different metrics at once. One main one and then one subgroup or sub thing is you have the MCC, which I'll explain in just a sec, and then STM and SQTM, which is just like slice turn metric and slice quarter turn metric. So this is basically by alg length. The MCC is an algorithm that you can adjust, and I'll have a video covering advanced MCC adjustments so you can customize the algorithm to your liking. but it basically it's analyzed what algs are preferred for many different algorithms like PLL, OLL, some ZBLL, CMLL, things like that. And so after that, it now is trained so that way it can try to, out of the algs it generates, it can then take those preferences and try to predict what cases will be better. So for example, you can see here, I have it set to sort by move count and then by how it predicts the algs to be ranked as far as alg quality. So here you can see for this case, we have two 11 move algs. And then here you can see this one that looks pretty nasty, F2, R2, F2, and then some U moves, or sorry, some F moves. That's kind of gross. And so it gives it a score of 20. While this mostly R alg, it's not great, but out of these two, you can see it has a lower MCC, which means the alg should be better between these two. And I think most people would agree this is better to do than that. So it's a pretty helpful, it's not perfect, but it does help sort algs, especially if you're genning algs for a very unexplored set or something completely new where the algs do not even exist yet. Alright, so that's what the sorting system here is. Show statistics, that shows the statistics down here. Show image options, these are the image options, and we'll cover this in a minute. I will skip that for right now. So here you can see there's no moves at the end that tell you what the post AUF is. So if I stop and clear this and then click show ending adjustments and restart the search, you will see it will add U moves onto the end for an AUF, post AUF. So I'll let this run for a minute and explain these other fields. In this field, show top whatever number solutions for each case. That just says how many algorithms do you want it to show you. That as far as the ranking by whatever metrics you have chosen. So here, this box here, show advanced MCC options. This will let you adjust the algorithm that ranks algorithms. So here you can see if we check this box, we have a whole list of different things you can adjust via sliders like wrist turn multipliers, push turns, destabilization, regrips, how bad you think E and S moves are, overworking, if you're doing like RRR, that kind of thing, rotations, stuff like that. But we'll talk more about tweaking advanced MCC options in a future video. So then finally, let's talk about the image options. But here you can see for this top alg here, or this first one, it now is adding like a post AUF to these moves that require it by having this setting on. So now the last thing to talk about is image options. So here you can see obviously an option for show images. I don't see why you would turn this off unless your puzzle is not supported. So here we have the first field, image type, and this is just for whatever puzzle it is you want to do. So for example, if I hit clear, I can, since we're genning ZBLL algs, we can set this to 3x3 top, and this is what the view will look like. Or if we set it back to normal 3x3. Here you can adjust the rotations. You can adjust the size of the images produced as far as like the pixel length. So maybe I want 100 by 100 images instead of 150. You can do that. You can also adjust the X and Y rotation. So maybe we want 50 degrees and a Y rotation of 30. We can get whatever angle view you want. So now let's talk about statistics. As mentioned before, it will calculate all the cases and then reduce down to be the final number of unique cases. Then once you get the full alg set generated, you will have different statistics. It will tell you how fast the final rate was for genning each case. It does tend to speed up once it gets going. the average move count coefficient or average ranking of algorithms, as well as the average move count in STM and SQTM, which is super nice. So down here we have the buttons for controlling the generation of algs. So here, obviously, start search. It will start searching for algorithms. If you press it again, it will stop the search. So let's let this run for just a moment. Because of my poor planning, I will say the masking lets you like change color schemes and stuff like that. Transparencies, those sorts of things if you wanted. So now we have some algs. So let's end the search here. We can use select output, and it will select the image and all the algorithms. And so then you can copy it all and paste it into an alg sheet if you wanted. That's up to you. I'll talk about how to import all the data into an alg sheet in a future video if need be. And then of course, clear output, it just clears everything from the solver. So I hope this tutorial was helpful. I know it's been long, but I wanted to cover everything you needed to know in depth. So I hope this was helpful. If you are confused about anything, leave a question in the comments and I will try to help out as soon as I can. And maybe other people that are joining in this video that do know how to solve or use this solver already could help you as well. I definitely encourage that. So yeah, any questions, comments, leave them, and I'll try to get with you when I can. Thanks for watching.